CS 113 students, this is Dr. Shiragi here to help you today learn how to compute sun angles based on Earth-Sun geometry. This is important because the sun angle has a lot to do with the amount of heat that we receive from the sun at any given location. It's probably your own experience that on different days of the year, the sun is different heights above the horizon. For example, in this picture, clearly this person experiences a sun angle that is greater in June than in December. And of course, we know that the weather is very different in June and December in terms of how much heat we're receiving from the sun. This is important because of the concept of beam spreading. Even though each beam from the sun contains the same amount of heat, when the sun angle changes, that amount of heat is spread over a larger area or a smaller area. For example, in the tropical picture off to the left, you can see that 1 unit wide beam of sunlight hits the ground and covers an area 1 unit wide. The sun is directly overhead, so there's no beam spreading. On the other hand, if you go with the picture all the way to the right with the igloo, you can see that a beam of sunlight of the same width as was in the first picture, because it's now coming in at a very low sun angle, spreads out over a large region, 2 units wide. The same amount of heat from the sun has to heat up a larger area, and so the amount of heating is less. The rays that we receive from the sun are effectively parallel. The sun, of course, sends out heat in all directions, but we're so far away from the sun that only the beams that are coming in basically exactly our direction hit the Earth. So they're basically parallel by the time they hit the Earth's surface. But that doesn't mean that everyone experiences the sun in the same direction. Here I've drawn 4 little people on the plot. If you consider the point of view of each of these people, you can see that the sun angle changes quite a bit at different latitudes on the Earth's surface. The yellow man, who's in the tropics, is experiencing the sun directly above him. He has a very high sun angle, whereas the pink man near the pole has a very low sun angle. The sun's rays are all coming from the same direction, but because of the curvature of the Earth, they're all experiencing slightly different sun angles, and therefore different amounts of beam spreading. As discussed in class, the Earth revolves, of course, around the sun in an elliptical orbit, although the fact that the orbit is elliptical is not what's important for the seasons and for sun angles. What is important is the fact that the Earth is tilted on its axis. Here I've highlighted the axis of the Earth, and you can see that in all cases the Earth's axis is pointing off in the same direction. As it happens at the present time in Earth's history, it's all pointing in the direction of the North Star, Polaris. Although that's just a coincidence, it just happens to be a bright star in the general direction the Earth's axis is pointing. Why does the Earth always point in the same direction? Because nothing is pushing the Earth to point in different directions. If we zoom in on the situation in June, when the Earth's axis is positioned in this way, you'll see that the northern hemisphere is tipped towards the sun. Now that doesn't mean that the northern hemisphere is closer to the sun than the southern hemisphere is. That's not what I'm trying to say here. What I'm saying is that locations in the northern hemisphere are experiencing higher sun angles than locations in the southern hemisphere. I'm actually highlighting here a very specific date. This is the June solstice. It happens about June 21st or June 22nd on any given year. And on this location, this is as much tipped towards the sun as the northern hemisphere is going to get. This is going to be the longest day of the year in the northern hemisphere. Longest in terms of length of daylight. The sun is going to be directly overhead at 23.5 degrees north, the Tropic of Cancer. That makes the Tropic of Cancer Earth's solar declination on June 21st. Remember, the solar declination is just the latitude at which the sun is directly overhead. Look at the North Pole. As the Earth rotates on June 21st, the North Pole is never going to be on the dark side of the Earth. At this time of year, the North Pole is experiencing 24 hours of daylight. Look at the South Pole. As the Earth rotates about the axis, the South Pole will never rotate into the part of the Earth that is illuminated. The South Pole then is experiencing 24 hours of darkness. Let's consider the situation then in the opposite, 6 months later in December. In December, the northern hemisphere is now tipped away from the sun. The southern hemisphere is tipped towards the sun. And in fact, I've highlighted a very special day here. This is the December solstice. It happens about December 21st or December 22nd. And on this day, the solar declination, the latitude at which the sun is directly overhead at noon, is 23.5 degrees south. 23.5 degrees south is the Tropic of Capricorn. So that on December 21st, the solar declination is as far south as it's going to get. This is the longest day of the year in terms of length of daylight for the southern hemisphere. In fact, you can see at the South Pole that the South Pole will never rotate out of the illuminated side of the Earth. So there are 24 hours a day of sunlight in the South Pole, whereas at this time of year, the North Pole is experiencing no daylight at all. In fact, all locations north of the Arctic Circle are experiencing no daylight at all on December 21st. So this will be the shortest day of the year in the Northern Hemisphere. Just to show an example of a equinox, let's look at September. September 21st and 22nd, I'm sorry, I guess this is actually March. March 21st and 22nd are examples of an equinox. On an equinox, all locations on Earth are experiencing a 12-hour day and a 12-hour night, hence the term equinox. March 21st and 22nd then are the March equinox. There's also a September equinox on September 22nd and 23rd. All locations on Earth are experiencing a 12-hour day on the equinoxes. The sun is directly overhead at the equator on the equinoxes. In other words, we would say that the equator is the solar declination on the equinoxes. For the equinoxes and the solstices, it's really quite simple to memorize the locations of the solar declination. But what if you wanted to know the solar declination on any given day of the year, like today? The answer is you need to use a diagram called the analemma. And this is an example of an analemma. There'll also be ones you can print out from your CV. I usually give them to you in class as well. But the analemma is just a type of calendar. And this calendar can be used to read off the date of the the latitude of the solar declination. The line that's drawn on the analemma is a type of calendar. You can see that it has months and days labeled on it. And you read around the analemma in the direction indicated by the arrows, following the shape of a figure 8. So you locate a date that you're interested in determining the analemma on this little calendar. In this case, we'll zoom in on the month of May. And let's just choose May 15th as the date at which we want to determine the solar declination. So on May 15th, then we read over to the y-axis of the graph, and we see that on May 15th, the solar declination is about 18.5 degrees north. In other words, locations at 18.5 degrees north will have the sun directly overhead on May 15th. So using the analemma is pretty simple. On the test, you will either be given an analemma, or on the test you'll only use dates from which the solar declination is easy, like the solstices and the equinoxes. The reason why you need to be able to determine the solar declination is because we're going to be computing sun angles. Remember, sun angle is how high above the horizon the sun gets, specifically at noon. We usually refer to this actually as the noon sun angle. And the equation for the noon sun angle is a pretty simple word equation. The sun angle is just 90 degrees minus the distance between your latitude and the current solar declination. Probably the easiest way to illustrate how to use this equation is to do a couple of examples. So here's the type of problem that would be very likely to be seen on the first test. Find the noon sun angle in Omaha, which we'll assume is about 40 degrees north, on September 22nd. I'm going to tell you that there's basically going to be a real simple 3-step process for solving this problem. Step 1. Ask yourself, where is the solar declination on September 22nd? Well, September 22nd is the September equinox, so we know that the solar declination on the September equinox is at the equator, 0 degrees north. Okay? Step 2. Step 2. Find the distance between your latitude and the solar declination. You said that the solar declination was at the equator, and the noon sun angle in Omaha was at 40 degrees north. So the distance between Omaha and the equator is 40 degrees. Finally, step 3, find the sun angle. Remember, it was 90 degrees minus that distance that we just computed in step 2. 90 minus 40 is 50 degrees. Therefore, on September 22nd, at noon, the sun will be 50 degrees above the horizon in Omaha. Let's do another example just to make the point clear as to how this is all done. Let's find this noon sun angle in Omaha, which again we'll say is 40 degrees north, on December 21st. Okay, simple 3-step process. Firstly, ask yourself where the solar declination is on December 21st. The December 21st is the December solstice. The sun is at the Tropic of Capricorn on that day, which the solar declination is at the Tropic of Capricorn that day, which is 23.5 degrees south. Step 2. Find the distance between your latitude and the solar declination. Okay, our latitude was 40 degrees north. The solar declination was at 23.5 degrees south. So the distance between 40 degrees north and 23.5 degrees south is 63.5 degrees. You need 40 degrees to get to the equator, and then another 23.5 degrees to get to the Tropic of Capricorn. Finally, step 3, find the sun angle. It's 90 degrees minus that distance that we just computed. 90 minus 63.5 degrees is 26.5 degrees. Okay. There are lots of types of questions I could ask you on the next test. Find the noon sun angle in some location on some date is a very common format for these questions. Another one I could ask you is, where is the sun higher on some date, location 1 or location 2? Again, I would give you latitudes, or they would be latitudes that you know, like the Tropic of Cancer or the Tropic of Capricorn. Or I could ask you a very tricky type of question. On what day is the sun angle 30 degrees in Omaha? Obviously, I can put different numbers and different locations into that question. Let's actually look at an example of that last type of question. When is the sun angle 30 degrees in Omaha? How would we solve something like this? Well, remember, your sun angle equation is sun angle equals 90 minus the distance between your latitude and the solar declination. We know that the sun angle is equal to 30, so 30 equals 90 minus this distance, meaning that the distance between your latitude and the solar declination is going to have to be 60. So that 90 minus 60 equals 30. So all we need now is to figure out, when is the solar declination 60 degrees away from 40 degrees north. Okay, well, that means the solar declination is going to have to be at 20 south. That's the only place on Earth that is 60 degrees away from 40 degrees north, right? 40 degrees from the equator plus another 20 degrees into the southern hemisphere will be 20 degrees south. Okay, so what kind of choices would I give you in order to solve this problem? Let's say these were your choices: April 3rd, September 1st, September 30th, December 15th. Now we need to figure out which of these dates would be the right day in which the solar declination is 20 degrees south. Now, perhaps I would give you an analemma, and then it would be fairly simple to solve. But if I didn't give you an analemma, how would we narrow this down? Well, first, right off the bat, we can rule out April 3rd and September 1st, because those days are during the summer. They are between the spring equinox and the fall equinox, or the March equinox and the September equinox. And so in both of those cases, the sun-solar declination is in the northern hemisphere. It can't be 20 degrees south on those days. On the other hand, it could be in the southern hemisphere on September 30th or December 15th. However, September 30th is only a couple days after after the September equinox, when the solar declination was at the equator. It's not very likely that only a few days after the September equinox, the solar declination would be all the way down to 20 degrees south. On the other hand, December 15th is only a couple of days before the December solstice, when the sun is directly overhead at 23.5 degrees south. Therefore, December 15th is a much more reasonable date to think that the solar declination would be 20 degrees south. Alright, so hopefully this has helped you understand this whole business of sun angles, which will help you on the homework and on the next test. If you have any questions, please reach me via email, or come see me during office hours, or call the audio blog, or whatever it takes. Just make sure you get your questions answered. This has been Dr. John Schrage, copyright 2006.